My name is Kristen Gonzalez Vega, and I am coming to you from Frisco, Texas. And today we are again doing AP Physics C, Electricity and Magnetism. I have my teaching partner with me, Roger.
Hello, everybody. This is Roger Siegel coming to you from Sarasota, Florida, where I teach physics and calculus at Pineview School.
All right, so tonight we have a very fun lesson. It's one of my favorite lessons to do. I wish we were in my classroom to do more, but we are going to talk about how we induce charge, polarization, electric fields, and field lines. So it's all kind of conceptual today and lots of fun. So again, my name is Kristen Gonzalez Vega, and we also have Roger with us from Florida. I wanted to go over a couple of things about the AP exam that we have learned. First of all, the date. Our AP Physics C is going to be on May 11th, both the mechanics and the E&M if you're taking both. The E&M is in the morning and the mechanics is after that. And you can see the times here on the screen for those corresponding time zones. As far as the timing goes, you're going to have 45 minutes for the exam. There's going to be 2 questions. You're going to have 25 minutes to read or respond to question 1. And then you'll have 5 minutes to upload your response. You're going to be able to either type up your responses or handwrite and submit those responses that you have handwritten. So after that time, you're going to move on to question 2. And question 2 is a 15-minute question with, again, another 5 minutes to upload your response. You cannot go back to question 1 after that time is over. And everybody is going to be taking it at that same time. A little bit more on those questions. Question 1, since it is a longer question, is worth a little bit more. It's 60% of the weight of the exam, and question 2 is 40%. The 2 types of questions, we have a long free response and a short free response. That long free response, you should be able to analyze representations of physical situations, determine scientific methods, analyze quantitative data and in graphs, and develop an explanation or a scientific argument. So that kind of gives you an insight on what kinds of things you can expect on question 1. It's going to have an emphasis on the Physics C, electricity and magnetism concepts, and not as much focus on the calculations portion. So we're going to start to incorporating a lot more of the conceptual type questions as we're doing this review, and you're going to see less and less of those calculation type questions. One example you can look at for this type of question is question number 3 on the 2017 AP Physics 1 exam. Question 2 is going to be a question that's going to assess your ability to design and experiment a lab and design and evaluate a lab experiment. Use graphical analysis of data to find physical quantities and identify physical sources of experimental variation. And that's going to be similar to question 2 on the 2012 E&M exam. Okay, so the units that are up for grabs on this are anything between 1 and 3. So that's electrostatics and Gauss's law. It is potential and capacitance, and it is circuits. So today we are going to go through in electrostatics how we can charge objects. You should be able to draw an electric field diagram from a single point charge. You should recognize that excess charge on a conductor resides entirely on the surface. That is a super important concept. Describe the process of charging a conductor by induction. Describe net charge residing on conductors during the process. And explain how a charged object can attract a neutral conductor. So if we look at these different types of charges, I'm going to give you kind of the basis of it, and then we're going to kind of go through and look at some examples. So we have 2 different kinds of materials. We have conductors and we have insulators. So in a conductive material, those electrons are free to move throughout the material. In an insulator, those charges are fixed in one place, right? So when we have 2 uncharged objects, let's take a balloon and a piece of hair. You can take those 2 objects and you can rub them together, and that friction between them will take electrons from one material and deposit them on the other. And there are some materials that tend to want to give up electrons, and there are some materials that tend to want to gain electrons. So hair happens to be a material that wants to lose electrons, and the balloon or rubber is something that tends to want to gain it. So when I rub these 2 together, this is charging by friction, and they're going to become oppositely charged. Okay, and so I could then bring this again close to the hair, and I don't know if you're going to be able to see this, but you can see that hair kind of raising up towards the balloon. So you can see that they have become oppositely charged. So that's charging by friction. That's one way that we can charge objects. Another one that we can do is charging by conduction. And so this is when you have an object that is charged, like my balloon now has a negative charge onto it. If I touch it to another conductor that is neutral, then some of those electrons will jump onto that material, right? Those electrons don't want to be close together. They want to be spread apart. So if I can give it an outlet for those electrons to go, they will go. We can charge by induction. And induction is when you bring a charged object close to a neutral object, not touching it though. And so that's going to cause a separation in the material, right? So if my balloon, let's say a metal sphere, and I bring a charged object towards it, well, then we know the hair is positively charged. So that means all of those negative charges want to be close to that positive charge, and the positive charges want to be away. So it's going to create a separation of charge in that material. If I bring another balloon close to it and touch it, then again, it'll give an outlet for those charges to move. And so those electrons can come in or go out depending on those charges. So even though those two conductors are touching, my actual charged object never touched it. So that's charging by induction. And then lastly, we have polarization. And polarization is when you have a charged object that's brought near an insulator and the atoms shift. So my wall, and I'll show you this with water, I have a video, but my wall is a little bit textured, so this doesn't work as well. But what you can see is the balloon goes slowly down the wall. I have a projector screen in my classroom that it's really good, it actually sticks to it. But we can see if the balloon will stick to it. If it not stick to it, you'll see that it'll kind of slowly coast down the wall. Ooh. Hey, it worked. Okay, so this is polarization. Now the wall is not a conductor, but the wall is made up of atoms that have positive charges and negative charges. So while my balloon has those excess negative charge, well, the atoms can shift in the wall where those positive charges will want to be close to the negative charges will be further away. So it creates that kind of separation of charge within that insulator where it's not charged, but there is that temporary attraction to it. Okay, so I have another simulation to show that too. So I'm going to switch my share here. And so I have a FET simulation. I have a neutral sweater. I have a neutral balloon, and I have a neutral wall. Right, so if I take my balloon, I rub it on the sweater, as you can see, we're picking up those negative charges onto the balloon. So the balloon is now negatively charged. My sweater is positively charged, just like my hair and balloon that we saw a second ago. If I let the balloon go when it's close to the sweater, what's going to happen? It's attracted to that because it's oppositely charged. If I bring my balloon close to the wall is an insulator. Those electrons are not going to actually transfer through the material, but you can see we get that separation of charge in the wall here, where those positive charges are close to the negative charges are further away, and we get that attraction between the wall and the balloon. That's the polarization part, right? So we had charging by friction, and we had polarization there. So if we go back, let's kind of draw some of this stuff out. So if we have two metal spheres, and we have them far apart, sphere X, sphere Y, and they're far apart from each other, and they are both at the moment neutral. But I'm going to bring a negatively charged rod close to that sphere X. I want you to think about what that's going to look like. If you have paper, I want you to get that out, and I want you to sketch what you think those spheres are going to look like as I bring that negatively charged rod close to it. And I'm going to switch over here to my iPad so I can actually draw it out better. So when they're far apart, let's zoom in here. I've got positive and negative charges. I'm going to draw like 3 positive charges and 3 negative charges on each one. And as you notice, those charges are spread out And we can't really see it here on this screen, but where those charges always lie on a conductor is on the surface of the material. So there's never going to be any charges in that space in the center of the conductor. It's always spread out through the surface. It can be the inside surface or it can be the outside surface, but never in the space between. In an insulator, those charges can be distributed throughout evenly, or we can have different charge densities. But for the conductor, remember, it's always on the surface, outside surface or inside surface, and both. So if I bring that negatively charged rod close to it, these are still far apart. That's not going to affect sphere Y, right? So sphere Y will still have positive and negative charges. But if we look at sphere X, those negative charges don't want to be close to that rod. So those negative charges are going to run away. I mean, I say that like they're actually people. We know they're not, but those charges are going to separate out away from that rod, and the positive charges do like that negative charge. So those positive charges will shift to the left side, still on the surface of that sphere. Okay, but then we can touch those two conductors together. And since they're conductors and those electrons are free to move, they sure are going to move. So those negative charges want to be as far away as possible from that negatively charged rod. So all of those negative charges are now going to lie on that right side of that furthest away sphere, which is going to leave us with a net positive charge on the other sphere. Right? It's the negative charges that are doing the moving, but since the negative charges are leaving the other sphere, there's now a net positive charge left. Okay, and then if we take sphere Y far away, still leaving that negative rod close to it, what are we going to get? Well, we're going to get still all of those positive charges on the left there, and we're going to get the negative charges on the right. But where are those charges going to be, since this far, far away, those negative charges don't want to be close, they're going to spread back out on the surface of that sphere. And then we take that negative charged sphere away, and now we can have that evenly distributed positive charge too. So we get two oppositely charged spheres in the end, right? So this is charging by induction. We never actually touched that negative rod to the sphere to transfer the electrons between the two, but we did touch those two neutral atoms together, neutral conductors together, and end up with those two oppositely charged ones. Okay, let's see what happens if we introduce a ground. So what a ground is as a way to create a path for those charges to flow. And on your house, at least here in Texas, I'm sure everywhere, we have, if you look around your house, you will see somewhere around the base of your house, a little green wire that's running from the house into the ground. And that's got to go like 6 feet deep into the ground. And what that does is it grounds out all of your wires in your house. And so if we introduce this ground, then we can look and see what's going to happen, right? So we have the same thing kind of here to begin with. We have our negatively charged rod that is brought close to these two spheres that are touching. So again, we're going to get positive charges here, and we're going to get our negative charge sphere on the other side. Okay, so if we connect that rightward sphere to the ground, then we're allowing for those charges to be able to leave or come in, right? We can also have negative charges coming in, we can have negative charges going out. In this case, since we have this negative rod, those negative charges are going to want to leave. So they can go out the ground, still leaving our positive charges here. Okay, so we remove that ground away, and we're left with all of those positive charges close here. And then if we take that negatively charged rod apart, then we have those positive charges that are going to equally spread out. Oops. And we separate them, they spread out on the surface. And then we're going to bring them closer back together and connect the ground now to the left side. So the positive charges are not going to flow out, but negative charges can flow back in. So if we look at that one on the left, we're going to have our negative charges coming in through that ground. And we're going to still have that right sphere. It's not touching anymore. Nothing's going on. That still has a positive charge. And that positive charge wants to be close to that negative charge. So introducing that ground allows for those electrons to flow either in or out of your material to create those neutral or same potential of the objects. Okay. The other thing we can look at is an electroscope. And I am going to stop my share here. And I'm going to move my camera so that we can see I have built an electroscope. Okay, and we can see that there are 2 aluminum foil leaves here. I think that's the best sideway view there. And so I have 2 foil leaves. It's connected to a copper wire that comes out and twists around here. So we have one nice kind of flow here. Let me back up a little bit so we can see a little bit more of it. And so what I want to see the leaves really close. What I'm going to do is I'm going to take my PVC pipe here. And I have some fur that I'm going to charge up that PVC pipe. And so you can see now those leaves and everything is neutral, right? All right now, there's no charge on anything. If I bring that PVC pipe close to it, I'll back up so you can see, I am not touching it. I'm only bringing it close to it. You can see those leaves start to separate. And so the reason that it's doing that is because even though it's neutral, there are still positive and negative charges in that metal. And so when I bring the negatively rod close to it, then those electrons want to go far away. So where do they go? They go down to the leaves in the electroscope here. And so when the electrons go down into those leaves, they don't want to be together, so those leaves are forced apart. So we can use an electroscope for lots of different things. We can tell what the charge on an object is. We can induce a charge on the electroscope and test out different things. So let's look at a diagram here. So we've got our electroscope. And as you can see, those leaves are spread apart, which means that electroscope has a charge. If I bring a negative rod close to it, we want to know what charge did that electroscope have to have in the beginning in order for those to, you can see what happens to those leaves. Did those leaves get closer together or did those leaves spread further apart? Well, if we compare the leaves here to the leaves here, well, these leaves have spread even further apart. So I want you to think for a second, what charge did this electroscope have to have on it in order for those leaves to spread further apart? Anybody know? Yeah, it's negative. I know you're all saying it at home. Because if we have, let's say, a net negative charge on the electroscope, well, if I bring this negative rod towards it, well, they want to go even further down here, away from that negative charge here. So there's even more negative charges on those leaves. So they have a further force, right? Remember, force is related to, if we have 2 point charges, KQQ over R squared. So the more charge we have building up on that object, the greater that force between those 2 leaves is going to be. Okay, so we remove that rod and it goes back to normal. So we bring a positive rod close to it. So why does, when we bring the positive rod close to it, why do those leaves now go whoop, closer together? Well, when we bring the positive rod towards it, we have some of those negative charges that are going to want to be close to that positive charge. And so we don't have as much charge left on these leaves. So there is still some repulsion. You can see there's still some separation between those leaves, but it's not as much because there's not as much, even though I drew them really big, there's not as much negative charge left on the leaves themselves. Okay. And let's look at just one more thing here. We have an uncharged electroscope. And so what we're going to do is we're going to bring a positive rod towards it. Then we're going to touch the electroscope with our finger. And then we're going to put the finger away and then remove the rod and look at the leaves. And so I want you to think for just a second at what you think the flow of those charges would be in each of those steps, right? What would the charge distribution look like in the first step? What would that charge distribution look like in each of these steps? So I'm going to give you just a second here to think about it. Okay, so we know it's uncharged. So that means there are positive and negative charge evenly distributed throughout here. Okay, so there is no force of attraction or repulsion between those leaves. They're just hanging there due to gravity, like mine was right now. But we bring that positive rod towards it and those leaves separate. So what does that mean? Well, that means that I have electrons moving up close to that rod on that metal top part. For me, it's the little curly Q here, but a lot of times you'll see like a metal sphere on the top of an electroscope. So negative charges are building up here. What do we have left then? Well, we have a net positive charge on the leaves. And so those leaves repel because they have a net positive charge on it. But if we go in this next step, if I introduce my finger here, let's kind of use this diagram. If I touch now the top of that, well, now I'm giving a path, right? That's for the electrons. So electrons can either flow into or out of. Well, if I have a positively charged rod close to it, what do you think wants to happen? Do you think the electrons want to leave? Well, no, they like being close to the positively charged rod. Those electrons are attracted to that. So that'll give a path for electrons to enter into the electroscope. So now we have electrons on here. So if I take my finger away, I have more electrons, but they're still built up close to the top. But if I take my finger away, we have a net negative charge left on the electroscope. Okay, so again, we have charged it by induction by touching that sphere when that positively charged rod is close to it. Okay, so I've got one more thing to show you here. I was playing around outside with my girls today, kind of showing them this. So we took a video, and it's not like as good as I usually can get it in my classroom, but you can still see here the example of polarization, because we all know from chemistry that water is a polar molecule, right? So if water is a polar molecule, we know it's made of hydrogen and oxygen. It has a partial positive and a partial negative side to it. So you'll have to excuse my quarantine attire here, my t-shirt that I rock every day. But I'm going to show you these two different views and see if you can notice what happens when we bring that charged rod towards that water stream. What do you notice? You notice that water bending around that rod. And that's because you have a shift in those molecules, and you have that positively charged hydrogen that likes to shift towards that rod, and you have those negatively charged oxygen molecules that want to shift away. And so you get that kind of curve in the water, which also helps us to see that polarization. Oops. One more time. All right. So the other thing we're going to talk about now is electric field. So around these charges, we have a region of space, right? And we call what around those charges, there is an electric field. So if we think back to gravity, around any massive object like Earth, we have the gravitational field. Well, the same thing will be true around charges. Around charges, we have an electric field. So what happens when we have a mass that's introduced somewhere where there's a gravitational field? Well, it experiences a gravitational force. Okay, well, if we introduce another charge into a region where there's an electric field, it's going to experience an electrostatic force. So the way that we draw these field lines is they always are going from high potential to low potential. And we'll talk about potential later, but really what that translates to is those field lines point away from the positive charges and towards the negative charges. We're all together, they are, meaning the greater the electric field, the further or the further away the charges are, the smaller the electric field. The more lines we have, that means the greater the charge, and the fewer lines means the smaller magnitude of charge. So if we look at some examples here on the left, we can see what the field lines look like between two oppositely charged atoms, or molecules. We can look at what it looks like if they have the same charge. So if it's positively charged, you can see all of those field lines pointing away in all directions. And you can see where there's no field lines here at all, that's where the electric field would be 0. Okay. We can also look at the electric field between two parallel plates or between a parallel plate and a charge. Oops, sorry. Okay, so those field lines point away from the positive towards the negative, and we can map out those field lines. And then we can also talk about what the potential lines would look like too with those, which is kind of what those dotted lines are, but we'll get into that a little bit more later. Okay, so here's a couple more. So what I want to know is A, what is the charge on each of these charges, magnitude-wise, positive or negative? And also, one of these has a greater charge than the other in each example. So can you tell me what the charge is, positive or negative? And can you tell me number 1 or number 2, which one has a greater magnitude of charge? So take a second and look at all 4 of those diagrams. Okay, so if we look at the first example here, the first thing we want to look at, which way are the field lines pointing, right? So if we look at these field lines, they are pointing away from charge number 1. That tells me charge number 1 is positively charged. And they're pointing away from charge number 2. That tells me it's positively charged. If I look at the number of field lines, look at how concentrated these field lines are very close to that number 1. There are a ton of lines really close together. That tells me that charge 1 has a greater magnitude of charge than charge 2 has. Okay, if we look at the second example here, now the field lines are pointing towards both those charges. So those are going to be negatively charged. And again, charge 1 has a whole lot more lines coming out of it than or going into it than charge 2 does. So it has a greater magnitude of charge. And if we look at the bottom, hopefully you'll recognize that charge 1 is positive and charge 2 is negative. And we can look at the number of field lines and see that number 1 has a greater amount of field lines around it. And then in the last example, we can see the field lines are going away from charge 2 and pointing towards charge 1. So charge 2 is the positive charge and charge 1 is the negative charge. Okay, so I'm going to turn it over to Roger. I have talked long enough. And Roger's going to go over some examples with us.
All right. Thank you so much, Kristen. You're right. This is one of the most fun units to teach, static electricity. I really do love it. All right. Well, let's take a look and see where we are. I'm going to start sharing my screen. Don't want to make that mistake. And so I'm going to be working in OneNote here. And so we just got through here looking at the electric field lines. Now, I love, being able to look at these concepts and kind of compare them with the gravitational field. We'll talk about that more later. All right, so here's our first problem. I think you're going to find this one's pretty easy. And so what we have is we've got these two metal spheres. They're initially uncharged, and of course they're sitting on these insulating rods. And now a negatively charged rubber rod is brought close to but does not make contact with sphere X. And then we're going to take sphere Y and we're going to bring it close to the opposite side and let it touch. So I'm just going to connect these for a second and imagine I'm connecting them with a wire. That's a stand-in for having this touch. And what's going to happen when that happens? Well, let's go ahead and kind of draw that whole thing out if we can in a series of steps. Okay, so the first thing is what we have is when I bring this negatively charged rod near this metal sphere, a lot of negative charges are going to go here to the other side, and that's going to leave the left side acting positive. And why is it positive? Because all these electrons that are free to move in this in this setup got as far away as they could. So the electrons here moved to the right. And what they did is they left this side with fewer electrons, which that made that side positive. Now, the next thing that happens is, let's say we'll connect them with a wire and or touch them. It's the same thing if we connect them with a wire. Now, these electrons, before the wire was here, the furthest they could get away from this was this far. But now look at what they can do. They can start to migrate. And so those electrons are going to start going as even further away. And they're going to, again, move all the way to the right. And so now what's happened is we've now left, now we've got excess positive charges on X and excess negative charges on Y. All right, and then what happens next is the rubber rod is now moved far away. So we're going to remove the rod. We'll take that away. And we'll go ahead and stop the spheres from touching. And so we'll go ahead and break that so they're not touching anymore. And so now the question is, what is the charge on each sphere? And so we can see that X is a positive charge, so one of these two, and Y is negative, which means it has to be that one. Okay. So again, thinking about what the charges are doing, what's causing them to do that, that's what we want to leave you with. We expect a lot of conceptual questions on your AP exam this year. All right, now this one I really love. I'm so glad we have it tonight because, and we're going to continue looking at this concept, but this is the first night where we're going to get to it. So we've got this charge of Q plus on a small sphere. There's my charge of Q plus, and it's lowered into this metal, it's a metal can, but it's insulated. So the metal only goes to here, and then the electrons can't go any further. If the sphere does not touch the inside of the can, there will be a charge on the outside of the can of what? Okay, so this requires us to draw a picture. And so I'm going to draw a picture of my can, but I'm going to emphasize the fact that the can has an outside surface and an inside surface. So I'm really super emphasizing this, right? The thickness of the can. And inside of this can, we've got a positively charged sphere. Okay, and we'll go ahead and put a plus charge there. All right, now this can is metal. It says it's a metal can, and that means it's a conductor. That means that the electrons that are associated with the atoms in the can don't have to stay with those electrons. They can, with those atoms, they can move anywhere they want. And so what I'm going to do is I'm going to draw a little line that's going to delineate the outside from the inside of the can. Now, you might argue, well, what about, where does the outside stop and the inside end around here? And we're not going to split any hairs over that. Now, one of the properties of a metal is that we can't have any electric field inside the metal. Now, if I just had this positive charge and there was no other charges, well, the electric field would go right through that metal, okay, if there were no other charges. But that's not what happens because there are other charges. And so what's going to happen? Well, since there's a whole lot of negative charges here to be had, right? There's no shortage of negative charges because they're electrons. They can go anywhere. And so what's going to happen is we're going to get a bunch of negative charges to kind of move to the inside of this can, to the inside surface. Now, the can started out as neutral. It started out with no charge. So what that means is, in order for the can to remain neutral, it has to have a positive charge on the outer surface. And so there's a positive charge that's now all around this outer surface. Now, if we look at the entire can, if you just look at the can, and I'm going to go ahead and I'll erase this in a minute, but I'm going to draw this kind of with a big hand. Okay. If you look at just the can, it's neutral because it has equal numbers of positive and negative charges. And if you look at the inside of the of the jar has now also been made neutral. And so that is because we have positive and negative charges. So let's back out for a second and see. The question originally said, it said, if the sphere does not touch the inside of the can, there will be a charge on the outside of the can of what? And that charge is going to be Q plus. And the reason I know that's going to be Q plus is because we're going to have Q minus, all of this together, all of these guys, they all add up to Q minus, which means these all on the outside add up to Q plus. Isn't that beautiful? Okay, I think I've got one more here, and then we'll throw it back to Frisco, Texas. So we have these field lines from 3 different charges. And so the first question asks us, what is the sign, the SIGN, of each of these? So I'm going to go ahead and take a look at that. Now we know that the electric field around a positive charge, the field lines point away from a positive charge. And if I have a negative charge, then the field lines point toward the negative charge. So all I have to do is look and see where their field lines are pointing toward. And so 3 is going to be a negative charge. That's going to be negative because it has field lines pointing towards it. And 1 and 2 are going to be positive charges because they have field lines pointing away from them. So that's both of these are positive. Okay. Now, the next thing that we're going to do is we're going to draw vectors at each point to represent the direction of the electric field at that point. This is going to be pretty easy because the electric field is always parallel to the field line at the point. So if we start with A, right here, if I look at this field line and this field line, I can pretty much estimate that the field lines are in that direction at A. Okay. And I could then look at B and this one. And so the field line again is the electric field is parallel to the field lines. Okay. At part C, that would be here. I'm not going to draw it right over the C because I won't be able to see the letter if I do that. But there's a field line there that's near the C. Okay. And then D is in this direction. There's D. And then E is in, actually, let me move a little bit off of there. And E is in this direction. So the direction of the electric field is the direction of the field lines. Okay, so we got that one. Now mark X in a position where the electric field is 0. So the electric field is 0, where the positive and negative vectors cancel out. And you can see that that happens about right in this area. So I'm going to go ahead and put an X there. And that's the spot where the field lines are 0, or the electric field is 0. So if I could put a charge there, it wouldn't feel a force in any one direction because all the field lines perfectly balance and cancel at that spot. Which charge has the greatest magnitude? Well, the way we get the magnitude of the charge is, remember, these lines are a stand-in for a density function. It's not like we have, there's electric field, there's no electric field. There's electric field, there's no electric field. No, there's electric field in a continuum around here. But by drawing the field lines, it allows our human brains it's a code for something. And so here, the closer the field lines are, that's code for how large the electric field is, the magnitude of it. And so if we look at this, if I put a little mark here and I go around, I can see that we have 1 starting there, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 arrows around this circle. Okay. And so I'm going to just put a little 24 there next to 1. Now I know that this isn't very much. 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 around 2, but 3 looks like it could have close to 24. Let me put a mark here and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. So that's 16. So the largest magnitude charge is charge 1, and the smallest magnitude charge is charge 2. Okay, and then what lettered point is the field the strongest? So the field is going to be the strongest where those lines, again, are closest together, are densest. And so I think if I look, it looks like it could be 2 places. I'm going to highlight each place. It looks like it could be C, they're pretty close there, or it could be B. And I got to say, it looks like B is denser than C. So I'm going to go ahead and put B is the place where the field is the strongest. I think that's going to get us there. So these field lines tell us a wonderful story. As Kristen said, tomorrow, oh, let's see, I forgot. One more, almost ready to wrap it up, and I got more to do here. In what direction would the force on a proton be if it were placed at E? So let's take a look at it. So the field line tells us the direction of the force on a positively charged object. So a proton is a positively charged object, and since the field is in this direction, then the force on a proton would be along the line of the field, not the motion, but the force, or the direction, if you might think about that, the direction of the acceleration. And now it says, the next part, oh no, that's not good. We are going to pause for a second and let my OneNote catch up. Okay. And I think Kristen, are you ready? Because I'm having technical issues, so I think we can hand it back to you.
Yeah, I am.
Okay, thanks.
So we're going to do one more example here to wrap it up for tonight. And I have kind of been looking through physics 2 problems that are good to use. So they gave us a physics 1 problem for kind of to show us an example of the type of question. So I've been kind of looking for some conceptual physics 2 problems, and I found this one that I think is still good for physics C concepts. So we have here a sphere. I'm going to zoom in on the words here. You can see there's a sphere hanging from a string. This is sphere 1. And we are investigating electrical charging of objects. So we have our conducting sphere that is suspended from an insulating string. And we're going to rub the sphere with a cloth to charge it. And we want to determine if the sign of what the sign on that charged sphere is. So we also have conducting spheres of various size that can be also hung on strings. And we have a pair of parallel conducting plates, each of which can be given a positive or a negative charge. So we want to describe a procedure the students could use to determine the sign of the charge on the sphere, including the measurements to be taken or observations to be made, right? So we want to know what the charge on this guy is. We have this other stuff. What could we do? Okay, so I'm not going to really pause just for time's sake tonight, but if you are going back and doing this, which I suggest you do if you're watching live, or if you're not watching live, take a minute to pause this and see if you can come up with a procedure on how you would determine what the sign of the charge is on sphere 1. So I'm going to say I'm probably going to use the parallel conducting plates. You can use the conducting spheres too, but I like the plates. So I'm going to take my plates and I'm going to put my sphere down into those plates, right? We know that it can be given a positive or a negative charge. So I'm going to connect those plates up to a power source, charge those plates up so one side's positive and one side's negative. Well, since that sphere is charged, it's going to be repulsed or attracted to that other side. So I look and see, well, if I put this sphere into it, does it deflect away from the positive side and towards the negative? Or does it deflect towards the positive side? And we know if it deflects towards the positive side, that it's got to have an oppositely charged charge. So it's got to be negatively charged. And if it deflects towards the negative sign, then that's got to be positively charged. So I'm looking for which way it deflects, and it will be, then that means it has the opposite sign. Okay, so then we want to know whether the same amount of charge is deposited on the sphere each time we rub it with the cloth, right? So I rub with the cloth, I give it a little bit of charge. Q. I rub it again the same way that I rubbed it before. Does it now have 2Q, right? We want to know, does the same amount of charge accumulate on there every time I use that cloth? So we're going to carefully rub sphere 1 with the cloth, the same motion each time. Then we're going to touch sphere 1 to an identical sphere, sphere 2. So we're going to introduce a second sphere here that's fixed in place. They then release sphere 1, and as you can see, the sphere 1 is going to be repelled up at some angle away from sphere 2. The students are going to measure the angle, theta, that the string makes with the vertical. They discharge the spheres and repeat the process, each time counting the number of times they rub sphere 1 and making sure the distance d between the spheres is the same. Okay, each time sphere 1 is rubbed with the cloth, the same amount q of charge is deposited, and that after n number of rubs with the cloth, the net charge on sphere 1 is n times q. Right, so we're going to accumulate n times q amount of charge. So we want to know what is the net charge on spheres 1 and 2 after they have been touched together. Indicate what property of the spheres is responsible for the distribution of charges, right? So I'm starting with n times q amount of charge. I touch them together and then separate them back out. So what would be the charge then on each one? Well, the charge is going to flow until they reach the same potential. And again, we'll talk about that again. But the other way you can think about it is look at the surface area of these spheres. We know charge wants to evenly distribute out across that surface of the conductor. So if these had, let's say, different sizes, if one conductor was much bigger than the other, well, I could spread more charge out on the bigger conductor than I could on the smaller conductor. So if we touched them together, then that charge would flow until they reached the same potential, but the charge 2 would end up having a greater amount of charge on it. But these two spheres are the same size. And so if they're the same size, then they are going to end up with the same amount of charge on each one. Okay, but we can't have more charge than we had to start with. So if we started with Q times N amount of charge, then that means that each one would have half of that amount of charge. Okay, so what property is responsible for that? Usually you can talk about the surface area. Since they have same amount of surface area, those charges are going to spread out evenly and each have the same amount of charge. Okay, the next part, we want to show that the angle can be related to the original charge Q on sphere 1 by the equation that the tangent of theta equals kn squared Q squared over 4m d squared times g. So if we look here, that comes back to those forces, right? And if I look at sphere 1, well, there's a force down because it has weight. It has a tension up because of the string. And since these are being repulsed, there's a electrostatic force pushing it away from sphere 2. But once it reaches equilibrium, well, we can look at what those forces would be in relation to each other. When it's in equilibrium, we know that I'm going to kind of write it down here a little bit. We know that the tension can be broken up into its x and y components. And so I know that the y component of tension up has to balance out that weight down. So that would be well, since theta is up in the corner here, that would be Ft times the cosine of theta equals mg. And I also know that the x component of that tension has to balance out the electrostatic force. So Ft times the sine of theta has to equal Fe. Okay, well, I don't like tension in there, so I got to get rid of tension. If I rearrange equation 1 for tension, then Ft equals mg over cosine of theta. And so then mg over cosine of theta times sine of theta, well, sine over cosine is tangent. So this leaves me with mg tan theta equals, we know the electrostatic force, we learned that equation yesterday, Coulomb's law, is K Q1 times Q2, and each of those charges is N over 2 times Q. So really, it's N over 2 times Q squared, because they each have that same charge, divided by our distance squared. And so then if we rearrange for tangent of theta, then tangent of theta will equal K times, now this becomes N over 4, which really the 4 can go on the bottom, times Q, N squared times Q squared over 4 times d squared. And then to bring the mg over, we divide, so times mg. So now we've got this relationship that we can use. And what we want to look at now is something that we have to do a lot in physics, and that is say, well, what could we graph in order to determine something we don't know, right? Maybe I want to know what that charge is, or maybe I want to know what the gravitational acceleration due to gravity is in that room, right? I love having my kids find gravity all different ways, but we can use this relationship to determine a constant. So if we identify these variables and these constants, the first thing I really want to discuss with you guys, though, since you guys are Physics C students, and I know that when you're reading this question, you're probably asking yourself, how can they keep that distance the same if they're changing the charge and theta is changing, right? So that's the first thing that stuck out in my head is how can we keep that distance the same? And so I am going to get rid of this d in my equation because we cannot keep that distance the same. The more charge you build up, the greater that force of repulsion is. They're going to be further and further apart. So I'm going to put in, instead of that, I want to look back at my triangle here. If this is L and this is theta, then instead of saying D, well, I can say the sine of theta is D over L. So then D is equal to the length of the string times the sine of theta. So then D squared is going to be L squared sine squared of theta. So really, tan of theta equals kn squared q squared over 4mg times L squared sine squared theta. So this is really my working equation. So anytime you linearize data, you do it the same way. There are some different ways you can do it. Sometimes you can say y equals mx plus b, and you can fit to that equation. What I like to do, and what I always tell my kids to do, is you identify your constants and your variables, you separate them to opposite sides, and then whatever you're left with on the left, which is the variable side, is going to be what you graph, and anything left on the right is the slope. So we're going to set this up real quick, and then I promise I'll let you go. So we want to look at what are our variables and what are our constants. So what did we change in the experiment? Well, we changed the number of times we touched that balloon with the cloth, which was n, right? So n is one of my variables. What else did that change? Well, the minute I change the number of times that I am charging that balloon, it's going to change that charge, which also changed theta. So we're going to say, we're going to keep that tan theta together, and the sine squared theta is our variable. So we put our constants on one side, variables on the other. So if I move my variables to the left, then I'm left with tan theta times sine squared theta over, I want to move my n squared over, and when I do that by dividing, so I'm left with n squared on the bottom, equals, I'm left with k times q squared over 4mg. So everything on that right is constant. I could find anything in there. Everything on that left is what our variables are. So we go back to the rule that's always true. Whatever's on the top goes on your y-axis. Whatever's on the bottom goes on the x. And whatever's left on the right is equal to your, well, what's y over x equal? The slope of your graph. So we could graph that. And if we want to know how we could tell if it has the same charge on each, if it does deposit the same amount of charge each time, how could we know that by looking at the graph? Well, once I graph that, if it deposited the same amount of charge each time, what should our graph look like? Well, that should be a linear relationship. Okay. So that's an experimental type question. I hope you have time to go back and really pause it and go through that and try to answer it on your own, because those are the kinds of things you're going to be seeing on the exam, is being able to say, to maybe write an experiment or analyze data. And so we're going to try to practice that a lot. But we are going to get you out of here. The only other thing I wanted to remind you of is the rest of the week, what we're going to talk about. So today we did inducing charge and polarization, electric fields, basics. Tomorrow, Roger's going to take us through how we can calculate what the electric field is due to point charges. So maybe 1 point charge or multiple point charges. Then Thursday, we're going to go into Gauss's law, which is kind of a shortcut to finding that electric field. And then Friday, we're going to do the other distributions, which line of charge, arc of charge, ring of charge, and how we can find the electric field due to those things. So I hope you enjoyed spending your evening with us and doing some of these fun experiments. And from Frisco, Texas, I hope you have a great night. Roger?
And from Sarasota, Florida, thanks again for joining us. Can't wait to see you tomorrow night. And thanks for playing.